Okay, so we're going to go over ratio and root test. So for these notes, I actually pre-annotated them, and I'm going to walk you through with the laser just to make the video a little shorter than the last one. All right, so let's start talking about the ratio test. So suppose we have a series, n from 1 to infinity a sub n, and we have non-zero terms. We're going to let rho, which looks like this p, rho, be the limit as n goes to infinity of the absolute value of the ratios of subsequent terms. So a sub n plus 1 over a sub n. And we have three different cases. So if we evaluate this limit and we end up getting a number less than 1 and greater than or equal to 0, this is a typo, then we can conclude by the ratio test that the series converges absolutely, i.e. it's absolutely convergent. If we get that this limit evaluates as something greater than 1, then we're going to say that the series is divergent. And then if we get 1, our borderline case, then the test is going to be inconclusive, and we have to pick another one. All right, so I want to walk you through the proof for why this is the case. So we're going to do the first one. And then the second one is very similar. If you are curious and want to try, you can try to prove the second one by yourself. It's a very similar argument. Okay, so let's do the first one. So we're going to assume we have a series with non-zero terms. We're going to suppose that rho is this limit, and we're going to assume that rho is something between 0 and 1. All right, so we have our assumption here. We're going to start by picking a small enough number, and we're going to call it epsilon, such that rho plus epsilon is less than 1. So whatever rho comes out to, we know it's less than 1, maybe it's 0.5. We're going to pick an epsilon small enough to where when we add it to 0.5, we get something less than 1. Okay, well, if we think about the definition of this limit existing, then we know that there is going to exist an n such that, essentially think of this as f of x minus L in the absolute value is less than epsilon. So we have a sub n plus 1 over a sub n in the absolute value minus rho, our limit. The distance between those two things is going to be less than epsilon for n greater than or equal to n. This is also a definition of the limit existing for sequences. Well, if I rearrange this statement around, I can get that the absolute value of a sub n plus 1 over a sub n is going to be between rho minus epsilon and rho plus epsilon. Remember, rho is like our L in that limit definition that we had earlier on. And if I rearrange this around, so essentially I'm going to take this piece and I'm going to rearrange it around, I get that the absolute value of a sub n plus 1 has got to be less than rho, see, it's just like L and I replaced it with an L. These are all rho's, rho, rho, rho. Row your boat gently down the stream. Here we go. Row, row, row. I got them all. Okay. Let's go back. So I'm going to rearrange this around. Essentially, I'm just going to multiply by absolute value of a sub n. And I've got that the absolute value of a sub n plus 1 is going to be less than rho plus epsilon times absolute value of a sub n. And this is for n greater than or equal to big N, same thing, same big N as over there. Well, that means that if I have a sub big N plus 1, because I'm starting at the first place where this inequality is true, a sub big N plus 1 in the absolute value is going to be less than rho plus epsilon times absolute value of a sub big N. Well, also, I have absolute value of a sub big N plus 2 is less than rho plus epsilon times absolute value of a sub big N plus 1. Well, I know that the absolute value of a sub big N plus 1 is going to be less than rho plus epsilon times absolute value of a sub big N. So if I substitute this in here, then I know that a sub big N plus 2 is going to be less than rho plus epsilon squared times a absolute value of a sub big N. And we could continue to do that until we get absolute value of a sub n plus k is less than rho plus epsilon to the kth power times absolute value of a sub n for k greater than or equal to 1. Basically, we were starting k at 1 over here, and we can continue up and keep doing this for any k greater than or equal to 1. Well, we have this comparison here between terms dependent on k. Keep in mind this big N is some fixed n. Rho is whatever our limit evaluated to, it's fixed. And epsilon is whatever epsilon we chose, but let's say we chose it, it's fixed. So the only variable here is this k and this k. So we're going to apply direct comparison test. Well, since I'm taking the absolute value of these terms, I have 0 is less than or equal to absolute value of a sub n plus k, which is less than or equal to rho plus epsilon to the k times absolute value of a sub big N. This is a geometric, our terms of geometric series. Our rho plus epsilon is like our r to the k, and then absolute value a sub big N is, remember, a big N is fixed. So a sub big N is some number, and we're taking the absolute value of it. So this is like our a times r to the n is kind of like the structure we have here. Well, since we chose epsilon such that rho plus epsilon is less than 1, we know that this is going to be a convergent geometric series, which means by direct comparison test that the sum of the absolute value of a sub n plus k is going to be convergent. Well, that means that the sum of, let's ignore the absolute value, a sub n plus k is going to be an absolutely convergent series. Well, if I just add back n terms, I've got the series from n equals 1 to infinity, a sub n. And so we have this is going to be absolutely convergent. All right, so that was the proof for ratio test. Let's go to root test. We're not going to do the proof for root test. This is the statement. We have let this series be a series again with non-zero terms. We're going to let rho be another limit, but it's structured as an nth root this time. It's going to be the nth root of the absolute value of a sub n. And then we have the same three cases. If our rho is between 0 and 1, we end up being able to determine that the series is absolutely convergent or converges absolutely. If rho is greater than 1, then we get that the series is divergent. And if we have our threshold case, the test is going to be inconclusive. All right, so really these problems just come down to setting up these limits, evaluating the limits, and then concluding your result. If you have a situation where you get this inconclusive case, that tells you that you need to pick a different test. All right, so here are 5 different problems I'm going to walk through in a moment. I would suggest that you pause the video and see how far you can get with each of these. But of course, that's up to you. So we'll do number 1 first. And like I said, I already wrote them out. So really honestly, pause the video if you don't want to see the solution. So we've got this series. Now, obviously, we've done ratio tests, we've done root tests. These are examples on those 2 tests. So from the context, you should know that we're going to apply one of those. But I want to tell you kind of what will key you in to applying ratio tests to this one. It's the factorial. If we see a factorial, I'm going to tell you, ratio test is probably the way to go. If I try to take the nth root of n factorial, this gets a little confusing to figure out what's going on there. So go with ratio test. So we set up limit as n goes to infinity of, this is my a sub n plus 1. Anywhere there was an n, I now have an n plus 1. So I had n factorial before, now I have n plus 1 factorial now. And I'm going to divide this by 2 to the n over n factorial. That's my a sub n, but that's the same as multiplying by the reciprocal. It might be easier to just start off by always multiplying by the reciprocal, but it's up to you. And then we're going to simplify. Notice that we have this n factorial in the numerator and an n plus 1 factorial in the denominator. If you think about n factorial and n plus 1 factorial, they're off by just a factor of n plus 1. So n plus 1 factorial can be rewritten as n plus 1 times n factorial. We end up getting that the n factorials cancel, and we end up with just this n plus 1 in the denominator. If we look at 2 to the n plus 1 over 2 to the n, those also simplify and give us just a 2. And so then we're evaluating this limit, which is very clearly 0, which is less than 1. And so by the ratio test, we have that the series converges, and even more specifically, it absolutely converges. Okay, for the next problem, we have the series 1 to infinity of n to the n over n factorial. Again, we see this factorial hints to us ratio test. So we go ahead and set up this limit. I have a sub n plus 1 times the reciprocal of a sub n. And we can start simplifying. So let me just explain how I grouped things here. I took this n plus 1 to the n plus 1, and I scooped one of those factors of n plus 1 right here, which leaves me an n plus 1 to the n on the right. This n plus 1 factorial in the denominator and the n factorial in the numerator simplify in a similar fashion to the previous problem and simplify to where I just get an n plus 1 in the denominator. And then I have this n to the n hanging out down here again. So now I'm evaluating this. The n plus 1's cancel, so really I'm just evaluating this guy. Well, I have different base, same exponent of n, so I can actually rewrite that as n plus 1 over n to the nth power. At this point, I'm dropping the absolute value because everything is positive here. Just a note, always start writing the absolute value if you're doing ratio or root test. You can drop them if everything inside of the absolute value is positive anyways, you can go ahead and drop them. So I could have dropped them here, I just didn't. All right, so we're evaluating this limit, which is just limit as n goes to infinity of 1 plus 1 over n to the n. We've actually done this limit in class, so I'm just going to skip to saying that this is equal to e. If you remember this, great. You can just say it's equal to e. If you don't, keep in mind you can do e to the natural log of this guy and use L'Hopital's rule. That's how we did it in class previously. Regardless of how you do this and get e is 2.7 something or other, which is greater than 1, which tells us that the series diverges by the ratio test. All right, next problem, we have natural log of n over n to the nth power. This is a very straightforward setup for a root test. And the reason that I know that, FYI, is because I have this raised to the nth power. When I take the nth root of something raised to the nth power, we end up just getting what was inside. And keep in mind, this had the absolute value on it, but since I'm taking n to infinity and natural log of n is greater than 0 once n hits 1, I'm good to assume that natural log of n is going to be positive for where I'm evaluating it from. This is a pretty well-known limit that it's going to be equal to 0, which is less than 1. And so we're good to say that the series is absolutely convergent by the root test. All right, number 4. Again, we have something going on with an nth power. So the root test is a very straightforward option. We end up just evaluating limit as n goes to infinity of 1 over n, which is again 0, which is less than 1. And so we have that the series is absolutely convergent by the root test again. And then we have number 5. So we have the series from 1 to infinity, 2 to the n over n to the 10. You could attempt a ratio test with this one if you want. I'm going to do root test. So I take the nth root. In the numerator, the 2 to the n, when I'm taking the nth root, simplifies to just a 2. In the denominator, the n to the 10, I'm going to rewrite this as the nth root of n to the 10. And if I take, just FYI, if I take limit as n goes to infinity of the nth root of n, this actually ends up being a 1. So this whole limit ends up being in the form 2 over 1 to the 10, which is just a 2. Which is greater than 1, which tells us the series is divergent by root test. If you're wondering how do I know that the limit as n goes to infinity of the nth root of n is 1, you can set yourself up for L'Hopital's rule. So we can write limit n goes to infinity e to the natural log of n to the 1 over n, which is limit as n goes to infinity of e to the natural log of n over n. If you apply L'Hopital's rule, this ends up going to 0, and so e to the 0 ends up giving us a 1.